Thank you for the introduction, Suvi. And so welcome everybody to today's optimization workshop. My name is Aki Kanerva. I'm a mentor at Elgin. I've also been doing game development for 17 years now at a virtual air guitar company, which I founded back in 2006. I've shipped 15 games. Most of them have been on consoles. So my roles have been pretty much wearing all the hats in an indie company, including programming, production, art direction, publishing, marketing, coffee making, you name it. So I have a lot of experience with both the technical and non-technical sides of game development. I mostly work in Unity, and I have also used Gamebryo before. So that's a short snippet of my history. You can probably hear my story in a different workshop, but that is not for today. So in today's talk, we will be talking about performance and optimization, which are like two views into the same topic. We're going to start off by talking on a general level, what does performance actually mean? This talk is intended for non-technical people and technical people. I will not be going through super technical details. Instead, I'm going to take more of a production and leadership view on performance, but also I'm going to go over how every single discipline in game development, including yours, whatever that is, also has an impact on performance and how you can contribute to it. We'll go through some examples of poor performance, how to identify different types of it to help with development. We'll talk about making design choices for performance. And then the other half of this workshop will be on optimization, which is the process of improving performance, which will include a brief look at profiling, making design level hard decisions about what to optimize, and how to include optimization as part of your natural development process. This will not be a workshop where you get lots of practical tips and tricks for optimization. That is for another time. But the real reason, which will become apparent later, is that everybody optimizes differently. It all depends on the project. However, I do have a bunch of tips and tricks in my back pocket, so if you want to hire me, that is possible. If you have any questions about terms I'm using, or if you don't hear what I'm saying, please ask in the chat. As Suvi mentioned before, this will be recorded, and there will be a longer question and answer session towards the end. So if you have any points you'd like to discuss further, please make a note of them and we will absolutely get back to them. And there will also be some interactive workshops, which we will begin with right away to get everybody warmed up. Okay, I'm going to use Miro for this. We're going to have a whiteboard for you. Can you, Suvi, share the link, please? Actually, I think I can share it somewhere from... Yes, there we go. If you would please click on the link in the chat and you will join the Miro I have prepared for this workshop. Do not move the pictures yet. Thank you. And so in here, you will see a screenshot of a game. This is Valheim. And I would like everybody to put some post-it notes on the below the image where you can see the different headers. And the topic of this little exercise is to identify and write down what potential performance issues might this game have in each of the various disciplines you see. And please feel free to enter anything related to your own discipline, but at the end of the session, I would like to see some stuff in each of these sections. Okay, looks like people are starting to converge on most of the biggest issues in the game. We'll give it a 1 minute more. Right, I am seeing plenty of interesting post-it notes here. Now we're going to continue the exercise. I'm going to reveal a different screenshot. This is Angry Birds. Please continue filling the all of the different disciplines with more post-it notes.
Is it cheating that I've actually worked on optimizing an Angry Birds game?
Absolutely not. All right, looks like we are about done. If nobody has anything more to add, we can take a look at the results. We have two very different games. One is a PC and console game, 3D, very traditional. The other is a very traditional mobile game, 2D, mostly based on UI, but it also has physics. What we can see here is that pretty much every discipline has something that affects performance. Narrative design here is showing a very empty box. I will come back to that later. There are also many other points about each of these disciplines that do not appear here. For example, on the audio part, we can have real-time audio effects that severely affect performance. Performance is also about load times, so audio format compression matters a lot. In the level design part, the camera view distance matters. In the UI part, input latency is a very important thing, especially in Angry Birds. Most of the things seem to be on the code and art side, which is to be expected. After all, those are the main disciplines that produce the bulk of the content for games. This is very good. There are lots of details here that I hadn't even thought about, like, for example, overlapping alpha layers, which is something I tend to forget myself. There are number of lights in a scene, things that are only apparent to level designers and artists who have been working with such things for a while. What we can see here is that every discipline has sort of accumulated knowledge about what affects performance, and people in different disciplines can already spot them just by looking at a screenshot. Things that are not apparent to producers or people in other disciplines. Right, I'm going to stop sharing the Miro board now and keep it for later inclusion in the video. Going back to the PowerPoint slides. So the first major point of this presentation is that everything and everyone affects performance. And it starts with design. Narrative design was an empty column in the workshop just now. And likewise, game design would have been if I had included it in there. That is because these disciplines do not produce any assets. However, they define all of the assets that the other disciplines produce. There's code, level design, UI, audio, and art. All of these things generate elements that cost performance. There are gameplay elements, game mechanics, interaction mechanics, input mechanics, game rules. There are systems that are not directly about gameplay, such as architecture, menus, loading, the audio engine. And then there are the actual assets, which are the 3D models, 2D images, textures, UI layouts, the levels themselves. And all of these stack up together to take a whole bunch of frame time. Each one of these things needs to be processed separately, and each one of these things takes some amount of milliseconds in every single frame. And that means every single discipline in game development has their part in determining how a game actually performs. That means optimization is everyone's responsibility, not just the programmers, not just the artists, but it is a part of project planning. Therefore, communication is usually pretty important because, as we saw here, some of these things require quite a lot of domain knowledge in a certain discipline in order to even realize that these things might affect performance, like alpha layers. If you're not an artist, you may not even be aware of what an alpha layer is. And no single person can know everything that affects performance in a game. The team does as a unit. And that is why communication is extremely important. Now, I have left out one important discipline, and that is quality assurance. While they do not produce actual content for the game, they are actually the most important discipline in terms of optimization and performance as part of a project, because it is the testers who routinely play the game, which developers usually don't have time for. Therefore, the testers are the best possible source of information about the performance of a game. And that is why it is important that testers have really good tools for analyzing, measuring, and reporting that performance. And by tools, I mean both the actual profiling tools as well as project management tools. And testers are in the perfect position to make frame rate measurements a daily routine, which benefits everybody. All right, now we move on to mythbusting, debunking some popular myths about what actually costs performance and what doesn't. Because performance seems to be this kind of weird amoeba-like subject that some things are slow and some things are fast. It's usually to do with code and art. And I will focus on art first. Performance doesn't mean the quality or beauty of your art. Bad art is just as expensive to render as good art. These two objects were taken from a polycount thread on the Dreamcast. Both of these objects here have about the same amount of triangles. One of them looks good, the other doesn't. But that doesn't matter or performance. They both render at the same speed. Performance also doesn't mean fidelity or detail. The difference between AAA and indie is that AAA studios just have a lot more people working on the art assets. And they have a lot more time for manual work in optimizing them. They don't have any secret formulae or expensive tools. They just have the manpower. Now, as an example, here's God of War. Now, if we compare this screenshot to the previous two, Valheim and Angry Birds, you can see that, well, actually there aren't a lot of performance-related problems here. There aren't many characters on screen. View distance is quite limited. Sure, the lighting looks gorgeous, but that's mostly post-processing and clever use of baked lighting because the environment is dynamic. So what AAA games usually have in common is that they follow established good practices for game and level design, where things actually are pretty optimized. With indie games, the palette of what you can do is so much broader that good practices don't yet exist. And they will never exist because every game is unique. Finally, performance does not mean style. Low polygon is something that I keep hearing being used in two different contexts. One is the art process, where an artist creates a sculpt in a 3D program, then applies polygon reduction, and the final exported asset into the game is called low poly. But low poly is also used to refer to a visual style. For example, here's a screenshot of Lonely Mountains Downhill, which is done in the low poly style, which means intentionally faceted objects, lack of detail in textures. However, all objects still have textures. And in fact, often in low poly, the details that you would normally put into textures are actually made with geometry. So it is quite possible and even likely that a low poly game actually has more polygons than one that uses a traditional blend of textures and polygons. So what we see here is that the polygon count of a game is also something that is kind of legacy these days. Yes, there are some limits, but it depends so much on the game that usually your performance issues are somewhere else entirely than the number of polygons you're rendering. So using a low poly style is not a choice for performance. It is a choice of artistic expression and style. What performance is limits. There's a limit to how many things you can have in your frame until you run out of frame time. You have 16 milliseconds to render things if you want to hit 60 FPS. Even less if you want to hit higher frame rates. Performance is loading time. Performance is the size of the package that you're delivering through the storefront or on disk. Sometimes loading time and package size are at odds. You have to make trade-offs between the two. Performance is input latency, which is completely different to a poor frame rate. Your game might be running at a good FPS, but still, when you press a button, if it takes too long for something to happen on screen, you have input latency. But both of these are usually communicated by testers and players as the game being slow. So it is important to recognize different types of slowness. And finally, there are memory limits, which doesn't affect your game's frame rate, It's just a hard limit. If you exceed it, the game will crash. And since there are so many different disciplines that contribute to performance, there are so many different limits, there are so many different design choices, even narrative choices that eventually lead to performance issues. For example, narrative can make a choice that we want to have the Battle of Helm's Deep, and we want to have 100 orcs or 1,000 orcs, when all the other levels only have 10 orcs. So in the end, design is responsible for everything that happens in performance. That is why profiling is the most important tool for actually measuring how much performance each element costs. And design is the discipline who are responsible for prioritizing what matters, what can we leave out, what do we need to optimize. And if you have not already done so, you should be using profiling tools. Yes, you can simply measure frame rate, but that doesn't really tell you what part of the game is causing a bad frame rate. This looks pretty intimidating. This is the Unity profiler. I know it looks intimidating, but yeah, you should look into it. You should get someone in your team who knows how to use it to teach the rest of the team. Because the more people who are able to use the profiler, the more people you have who can drill into the issue and maybe fix it themselves, even if they are not programmers. The other type of profiling is to measure frame rate and then program your own debugging tools for switching features on and off, maybe changing the light mode at runtime. That way you can try out different types of options and see how they impact the final frame rate. Because as great as profilers are, they are not good at telling you what the potential impact of a change is. For that, because everything interacts with each other, you might find out that a certain process takes up 3 milliseconds. If you optimize that to 1 millisecond, you might save 2 milliseconds, but it might also have an impact on a bunch of different systems. So the only final number you can trust is the final frame rate of the game. Next up, we are going to talk a little bit about the different types of frame rate issues you might see in a game. This is for everyone to identify what might possibly be going wrong and who to report to, and maybe even fix it yourself, because the game is slow, isn't very helpful. And now I'm going to share a little video from a game called Air Guitar Warrior, which I have made at Virtual Air Guitar Company. It is a side-scrolling shooter that normally runs at a very smooth 60 frame rate, 60 FPS. Here we go. Yes, that is me playing a flaming air guitar while riding a cyber dinosaur. And when I press play, you will see that the game is running very nice, very smoothly. And then I have simulated some frame rate issues for you to observe. Now we have a constantly low frame rate. Every single frame takes long to render. This is about 10 FPS. Now observe the difference when we get to fluctuating FPS, where the game at some point runs smoothly and at other times runs at a low frame rate. Kind of this growing motion. And finally, we have spikes where we have individual slow frames in the middle of good performance. All of these look different, but all of these could be described as choppy or slow. That is not very helpful when you're a tester. Right, going back to sharing my slides. There we go. So these three core types of frame rate issues illustrate different problems. It is actually quite rare to see frame rate that is constantly very low. It's usually caused by a bug somewhere that you're accidentally doing a for loop 1,000 times instead of 10 times. Because a constantly low frame rate means that something is exactly the same way in each frame. It can also be caused by systems that always run regardless of player input. Sometimes it might also be post-processing because you're always processing the same amount of pixels regardless of what's happening inside the game. Most common type of frame rate issue is fluctuating frame rate, which means that the user's actions inside the game are causing sometimes there to be slow down, sometimes the game runs fast, depending on what the camera is pointing, for example, or whether they are just starting combat with a lot of enemies or if they are finishing combat with a few enemies. Games are unpredictable. It doesn't really help that you know that the frame rate is fluctuating, but it does tell you that it's probably not, it's probably related to interaction. And that means you need to do some profiling. Spiky FPS or slow frames, these are usually caused by reactions to various events. For example, if you have a game where you press a button to fire a gun, then the moment you press the button, then the gun needs to produce audio, needs to produce particle effects, needs to generate a bullet, needs to do hit detection. All of these things may happen inside a single frame. And it doesn't happen in every frame because the gun is not shooting in every frame. Likewise, if you have physics, sometimes when things collide, you have a lot of code in that single frame where the collision happens, but not in other frames. Or it might be due to systems like garbage collection. Okay, this slide is in the wrong place because we already did the workshop. So we move on to part 2, optimization, which is the process of improving performance. We've talked a lot about what causes performance issues, but what do you actually do about them? Which seems to be a huge worry among producers and leaders that I've talked with. They see that their game's performing poorly. They don't know what to do about it. They don't know whether they should focus on it right now or maybe later down the line. And they begin to ask, okay, well, where can I find like some guides for optimization? What do I need to do to make the game run faster? But the thing is that there is no right answer. Nothing is slow or fast on its own. Performance is about stacking force multipliers. Let's take a look at an example. We have a game with an orc enemy. How much frame time does an orc cost? The orc has a bunch of modules. There's audio, particle effects, 3D model, animation, health bar and other UI stuff. There's pathfinding, there's AI code, there's all sorts of related subsystems and code. All of these things stack up in order to contribute to frame time. A single orc is fine. But if we want to have 6 orcs, we're out of frame time. Oh crap, the game is running poorly. What do we do now? We begin the process of optimization. We start off by optimizing one element. Maybe we take a look at the pathfinding and decide, okay, let's do it better. Since we are optimizing one algorithm that is multiplied 6 times, even small savings can stack up. However, the weird thing is that we can also optimize a different element and still get to the same result. Maybe we optimize the 3D model of the org so that it is faster to render. That gives more time for the pathfinding. And we are, again, at the same frame time. What this means usually is that everybody needs to contribute. All of the different disciplines, code, audio, design. For example, design may decide that maybe we can deal with fewer orcs on screen. Maybe we can improve their AI a little bit so that it doesn't cost a lot, but drop their number so they're smarter. Or maybe design can decide that, yeah, sure, we'd really like to have the feel of a mass battle, but the orcs don't have to be very smart, so let's drop the pathfinding. Or we can cheat. Turn on GPU instancing and suddenly we can have 1,000 orcs. Actually, let's go back to cheating. Cheating is actually a perfectly valid method of optimization. There are 4 different ways to approach optimization. One, probably the hardest one, is to work smarter. This means where you're learning your own discipline, learning the tips and tricks, making better code, spending more time on improving models. As I touched on before, you can put more work. Like, for example, you can spend a lot more time manually reducing the polygon count of your 3D models. Or you can spend a lot more time writing code that is has more lines, but performs better. Another way to look at optimization is trade-offs. And finally, there is cheating. So if we take a more detailed look at smarter work, it can be about learning ways to code better. For example, caching your transform component in Unity is one of the basic optimization things that pretty much everybody can do. After that, there are no guarantees. More work means applying the same optimization to every single script that you have implemented. That's a lot of manual work, but it pays off in the end because even though you are not working smarter, you are still putting in the effort that improves frame rates eventually. Trade-offs means something for the design and narrative team to think about. Do we want to have smarter enemies or more enemies? Sometimes you have to choose. It should not be the programmer's task to choose which one you want. Sometimes you want to balance load times with package size. Sometimes you really want to have better physics. Sometimes you have to say that, okay, maybe physics doesn't have to be so very impressive if it gives us a better frame rate. Trade-offs is not something you can learn to do, but it is something that every game developer can do and should do. Therefore, optimization is not like other disciplines. It is a process that you apply to your own discipline. And finally, there's cheating. This is kind of related to work smarter, but I wanted to highlight this as a separate idea. That sometimes you just do things in a way that reduce the quality in a way that the player doesn't see it. This is a screenshot of a Unity asset that helps you generate billboards, or also called imposters. So instead of having a 3D model of a house in a scene, you put a picture of a house in the scene. Obviously, this approach fails if you need to be able to walk around the house, but if it's just in the background, then it doesn't actually have to be a 3D model. This sort of out-of-the-box thinking is an integral part of optimization because it can be very efficient and effective. With a small amount of work or a medium amount of work, you can reach some really good savings, and it will only have a very small impact on the experience to the player. Right. Here's a common question. My frame rate sucks. Where do I begin? This is something that game developers ask themselves quite often. Producers have to think about this. Well, okay, we have a performance issue. How should I organize the next sprint in order to get it resolved? For many people who are doing the actual production work, like programmers, artists, level designers, they are very close to the thing that they are doing. They probably have a pretty good idea of something that's like, yeah, that's a real piece of spaghetti code. That AI there. It's yeah, I know it use a lot of optimization. I'm sure it's a real mess, and that is the apple. It's very shiny, very bright, very red. You really want to go and grab it. But what you actually want to do is analyze how much work will it take to reach that apple. Sometimes you might want to go for the low-hanging fruit instead. Sometimes you might want to go click on the lemon checkbox that says GPU instancing. If you forgot to turn it on, then you might have a really bad frame rate. And turning it on takes a few seconds. It might not be as effective to the total frame time as fixing the whole AI code would be, but the amount of work you put into it to reach that FPS saving, that is a good return on investment. Therefore, the impact of optimization should always be analyzed by performance gain you get divided by the work hours you put into it. Refactoring that whole AI might actually take 2 months. Sure, it might save you 5 milliseconds in the end, but that should be taken as a last resort. Always start where the going is easiest. The next question, to sum up all of these together, is when should I optimize? Because you can optimize too little and you can optimize too much. It is difficult to find the golden road between the two. Programmers like myself love the idea that everything should be optimized as you go, preferably before you have even profiled it, because, well, code should be elegant, code should be beautiful, code should be efficient. But that can lead to paralysis, where you get nothing done because you're optimizing everything before you can proceed. So premature optimization is a bad thing because you don't actually know until you've profiled how much does it really affect frame time. Spaghetti code may look really bad, but it might not actually be inefficient in the end. So what you want to do is profile early, profile often. When you do optimize, always base it on profiler data. Measure that frame time. See what processes actually take up your frame time and optimize those things. And this does not mean that you shouldn't do basic optimization. Basic optimization is different from premature optimization. Basic optimization means using good practices as part of your daily work. They are the little things that make a very small difference, but they don't cost a lot of work hours. Writing a for loop instead of a for each loop, using cached transforms, using a texture atlas instead of individual textures. These are the little things that should become part of your daily routine, so that optimization happens iteratively along the way. Let's take another look at that. The iterative development process. Game development isn't a waterfall, and it is not agile. It works in cycles. You make stuff, test stuff, then you go back to fix the stuff. Optimization should be a part of this cycle where you hand out what you've done over to testing, and while they're looking for bugs, they also look for performance issues. Optimization should be part of a single sprint. It should be allocated as a portion of everybody's time. We look at what game development people actually spend their time on. Only about 20% is the actual execution of your own discipline, whether it's programming or modeling or animation and so on. 20% of it is communication with your teammates, 20% of it is planning, 20% of it iteration. That is what happens when inevitably your plans do not work like you planned. And optimization is actually a part of the daily routine, or it should be. So when you're doing sprint planning, when you're estimating tasks, remember that optimization should be included in the natural work process. It is not something that you do at the end of the project. Oh yeah, sure, we'll have time to make it run faster, because no. You may find out that you need to change the design in order to optimize. If you leave this at the end of the project, that's going to be a big problem. And optimization is something that belongs to every single discipline, even the narrative designers, because the writers are those who define what assets the game needs. Now, for example, let's say you are designing a role-playing game with a bunch of quests, and you're writing quests. For those quests, you may need you may come up with ideas like, okay, I want this quest to have a couple of NPCs, this quest needs an inventory item, this quest needs an object in the world that I need to go and activate. Each of those things requires implementation and execution by at least one artist, programmer, level designer, and so on and so forth. As a writer, you don't know which of these things cost performance. So you should be ready to prioritize and argue that, okay, having a world object is super important. We can't deal without it. But having inventory objects, well, sure, I can write it in a different way. What this means is that planning these things should be the responsibility of the whole team, because everybody in their own discipline knows what costs performance and what doesn't. So again, to reiterate, communication is key. All right. Now let's sum up and go to our Q&A. We talked a little bit about how everything and everyone affects performance, how all disciplines have a role in performance and optimization. We talked about myths, about what costs performance and what doesn't. We talked about various limits that define performance. As long as you remain within these limits, you can do anything you like. We talked about identifying different types of frame rate issues, We talked about frame time and how it is not always obvious that thing that looks expensive may not be the right thing to optimize, and how everybody, all the different disciplines, need to contribute. Talked about the 4 different methods or approaches to optimization: smarter work, more work, trade-offs, and cheating. We talked about low-hanging fruit and bypassing the obvious. And we talked about how to integrate and lead optimization as part of the iterative development process. All right. I believe this is the end of my very long monologue. So we're going to stop recording now and let's discuss and talk.